Okay, so welcome everybody on our seminar. So our speaker today is Cong Zhang, who recently was on the postdoc in FAU in Erlangen, Nuremberg. Before, he was also quite long in our institute, and now he got a tenure track position in Beijing Normal University in Beijing. So, and he will tell us about black holes and covariance in effective quantum gravity. So please, you can start.
Okay, so thank you for Wojtek to introduce me, and it's my pleasure to come back at the University of Warsaw again to give this talk about our new work. And this is a work in collaboration with Professor Lewandowski, Professor Ma, and Professor Yang. So this is the work. So we already put the paper of this work in archive, and you can just go there and to see it. And the first is like the motivation. So there are a lot of reasons to make us believe that general relativity is not the final theory of space-time. So in order so because of this, so we need to modify gravity. So it's require us to relax one of the fundamental hypotheses of the Lovelock theorem to so this Lovelock theorem makes the Einstein's GR unique. And for instance, we can consider this alternative theory with extra field, non-local theory with Hare derivative, or this called a minimally modified gravity. So in this minimally modified gravity, so this four-dimensional diffeomorphism covariance is broken, but they consider this spatial diffeomorphism covariant. And in addition to these options, so in our work, we attempt to explore another approach. So in this approach, we will abandon the existence of an action in terms of the metric tensor, but we want to still maintain the four-dimensional diffeomorphism covariance. So why we want to consider this approach? Because this approach is particularly relevant when we consider canonical quantum gravity model, so which leads to a semiclassical theory of gravity in the Hamiltonian formulation. And another motivation comes from loop quantum black hole models. So in loop quantum black hole models, now people consider this classical spherical general relativity. And then, so people just choose different coordinates for this 3+1 decomposition, and we call it different gauges. So for instance, you can consider the interior of the black hole and choose the Schwarzschild coordinate, and then you will get this homogeneous model. And you can also consider a coordinate in which this special slice passing through the horizon. So consider such model, you will get a spherical symmetric GR. So you choose different gauges, and you will get this model 1 and model 2. And they are diffeomorphism equivalent because we know this classical GR is diffeomorphism invariant and a different choice of coordinate. And then people just do loop quantization. So they get this quantum model 1 and also some quantum model 2. However, the point is like this quantum model 1 and the quantum model 2, they are not diffeomorphism equivalent anymore. So from this result of this figure, so we can see that the loop quantization procedure we used so far in the black hole model is actually not covariant. So in our work, so we will relax the reliance on a specific quantization procedure. So what we are going to do is to investigate how the requirement of covariance constrain the possible forms of a quantum theory. So this is actually, I want to emphasize, so this work is not in a specific quantization procedure. So we just want to consider like how this general covariance constraint the choice of quantum theory. So what we are going to do is to consider an effective theory in the Hamiltonian formulation. So in this effective theory, the dynamics is described by a diffeomorphism constraint and the Hamiltonian constraint. So we will leave the diffeomorphism constraint as its classical form. So this is actually usually do in loop quantum gravity, loop quantum black hole models. But we will assume that this Hamiltonian constraint is an effective one. So in this effective one, there are those quantum gravity effect encoded. And then we will assume this constraint algebra. So this is like the classical one. However, we have this factor mu. And for this factor mu equals to 1, it is this classical algebra. But we will assume this 1 in general may not be equals to 1, account for this quantum gravity effect. And then we just ask the theory to be covariant to say like what should be the condition for this effective Hamiltonian H if. So one thing is like why general covariance is an issue here. This is because like we prefer this Hamiltonian formulation of GR, and in the Hamiltonian formulation of GR, it depends on the 3+1 decomposition. So it seems like the 3+1 decomposition could broken this general covariance of this 4-dimensional general covariance. And this is actually a general issue in all effective quantum gravity models in this canonical formulation. So let us go to some details. So what we are going to consider is the spherical symmetric model. And in this spherical symmetric model, so these mathematical structures are as follows. So here we have this spacetime manifold in this left-hand side. So it is a 2-dimensional manifold because we consider the spherical symmetric case, and there is only this time direction and the radial direction relevant. So we have this 2-dimensional manifold, and because we are going to consider this canonical formulation, so we need this 3+1 decomposition, and this 3+1 decomposition need us to introduce a field, a scalar field T, and this is used to formulate this manifold, and also a vector field TA, and they satisfy this relation. This vector field TA is used to identify points in different spatial slices. And in this canonical formulation, we also have the phase space. And in this spherical symmetric model, the phase space contains the field Ki and the EI. So I is from 1 to 2. Ki is related to the extrinsic curvature, and the EI is related to the spatial metric. And the points like Ki and the EI, they are actually the field on the initial slice sigma 0. But in the phase space, they are actually a point in the phase space. And the dynamics is encoded in the diffeomorphism constraint HS and the Hamiltonian constraint H if. And then we just want to solve the dynamics to construct a space-time matrix. So how could we do? So first, so we have this constraint surface, and we find a curve in the constraint surface satisfy the Hamiltonian equation. And so in order to write down this Hamiltonian equation, we need to choose a lapse function n and a shift vector nx, and then we so
now we have quite bad connection, I think.
Yeah, I think it's on his side.
Okay.
Ja nie słyszę głosu.
Okay, I wrote to Cong, and I think
So
So?
can you hear me now?
yes, we can.
Okay. Okay. Yeah, so I think this is the problem of the internet. So sometimes you cannot hear it. So you can hear me now, right?
Yes.
Yes. Okay. Okay. Good. 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 So
So
can you hear me now?
yes, we can.
Yeah. So I think this is the problem with this internet. Sometimes it happens. So people cannot hear me. So where should I start?
Maybe from the beginning of this slide, it would be safer.
Okay. So the point is like now, so we just want to solve the dynamics and construct this space-time metric and the space-time. And what we are doing, so here, so we just under constraint, we just find the curve. We just find the curve, this red curve satisfying the Hamiltonian equation. Satisfying the Hamiltonian equation, and in order to write down this Hamiltonian equation, so we need to choose a Laplace function and a shift vector. Okay, and the points like as I said before, so each point on the free space is actually a field on the special slice. So we can just treat this Ki of t and the Ei of t as a field on these t slices. So then we will just get a space-time field. We just get a field on this manifold M2 Ki of Tx and the Ei of Tx. Okay, and then we can define this metric to be this one. This is the classical expression of this metric. Okay, and then what do we mean by general covariance? General covariance means like as what I said before. So here we need to choose some Laplace function and a shift vector to get this solution. So general covariance means like if this metric ds square, so it's the same up to a diffeomorphism for different choice of n and ns and nx. So the answer actually depends on the structure of the constraint algebra. So let us say how could we say if this theory is covariant or not? So we just do an infinitesimal transformation for the shift vector and the Laplace function. Okay, so here this epsilon is just a small parameter, and then we have this one. So yeah, so here it is a little bit complicated because I want to have a simple form here. Okay, and so once we do this transformation, so there is this alpha and also a vector field and a vector field beta. So you can see we actually have a scalar field alpha and a vector field beta to parameterize this the transformation of this nx and n. So yeah, and then so once we do this infinitesimal transformation for the shift vector and the Laplace function and this k and e, they will be transformed like this. So here it is just the Poisson bracket of this Ki with respect to this H smeared by alpha times n, and this diffeomorphism constraint smeared by this beta by this vector field beta. And it is also the same for this EI. Okay, so once we do this transformation, we will get the transformation for this Ki and EI like this. And then, so we can calculate what will be the transformation for this matrix. And so you can just substitute this result into the expression of this matrix. You will get something like that. So here there are some quantity delta 1 and delta 2. So it is some complicated stuff, but what we need to know is that so delta I equals to 0 if H is independent the derivative of this Ki. Okay, and so as a consequence of this result, we will know that the classical theory is covariant. Why? Because in the classical theory, so this H is independent the derivative of Ki, and also this mu equals to 1. And then we will get this expression. So that means like this means like infinitesimal gauge transformation. And the right-hand side is the infinitesimal diffeomorphism transformation. So gauge transformation corresponds to the space-time diffeomorphism transformation. So this classical, the classical theory is generally covariant. But in general, we don't have this result. You can see, for instance, if mu is not equals to 1, so this will not be true, and then the theory will not be covariant anymore. And to fix this problem, this general covariance issue in general, so what we do is first we just modify the expression of the matrix. So we define a new matrix, so which is this GAB mu. Mu is used to tell people that this is the new matrix. And so why we do this modification? So the point is like we can always do some modification, right? We just do some modification such that this GAB of mu equals to this classical theory where mu equals to 1. So this classical theory will be included, and then we will have some more choices. And then the second is like we just want to find some effective Hamiltonian constraint which gives a covariant theory with respect to this new matrix GAB mu. So how do we modify this matrix? So what we are doing is like we consider this constraint algebra. So in this classical theory, this mu equals to 1. And this part, so this E1 and E2 2 power minus 2 will have this geometric interpretation of the spatial of the x component of the spatial metric QXX. So we therefore introduce an effective metric GAB mu defined by this one. So with respect to this metric, you can just calculate the corresponding XX component of the spatial metric. It will be this one, and it is the same as this one. So because of this, so that means like we want to keep the geometric interpretation of this constraint algebra. So we just do modification for this metric to be this one. So the geometric interpretation is preserved. And then we just do calculation as what I did here, and found this theorem. So we suppose this constraint algebra, and we define this effective matrix. Okay, so we want this theory to be, if this theory is covariant with respect to this effective matrix, so there will be these two sufficient and necessary conditions. So the first one is that, so this H if is independent the derivative of this K1. It is independent, sorry. So I forgot something here. So it should be like plus, this will be E1. d omega square. Okay, so this is the radial. This is the no, not radial, but the angular part of this metric. Okay, because we want to have a four-dimensional metric. Okay, so the first point is like H if must be independent of the derivative of this K1, and this is actually from the covariance of this part, the covariance of this part, and the
We lost the audio again.
So, okay.
okay. So where should I start?
I think so. You had part of this theorem one already. You were so you also there is addition to S mu, but okay. So we remember that. I think
Okay.
theorem one you started to describe.
Okay. So in this theory one, so we just suppose the constraint algebra this one, and then we define this effective metric. So we want this theory to be covariant. That means like the diffeomorphic, the canonical transformation is equivalent to the diffeomorphism constraint. Okay, and then there are these two conditions. The first one is that this H if is independent of the derivative of K1, and the second condition is this one. So I want to give some explanation on this equation. So the point. So here this S, it is just this E1 divided by E2 square. Okay, and what is this means? Okay, so here, yeah, so here it is a little. So let us say that we have some variable like which is canonical conjugate to this mu s, okay, and then this H if. So if this H if depends on the derivative of this canonical conjugate variable of mu s. So and then when we do this Poisson bracket, so we need to do the integration by part, and then this will not be true anymore. However, if this H if is independent, the derivative of the canonical conjugate variable of this mu s, so this one will be true. And this is the explanation of this equation. Okay. Okay, so now what we have is like we first have this constraint algebra, and then we have these two covariance conditions, and we aim to get the expression for this effective Hamiltonian constraint. And the point is that this effective Hamiltonian constraint is a scalar density with weight 1. And you can just go to analyze the scalar the weight of the density of this E and the K. So this E2 is a scalar density of weight 1. So that means like H if can always be written in this form. Here F is just a scalar field on the special method, on the special manifold. Okay, so F is a function of this scalar on the scalar manifold. That means like F is a function of those basic scalars of this Ki, Ei, and the partial Xei, and so on. So here the point is like, so F shouldn't depend on the derivative of K1 because of this requirement. And the second is like because of the form of this constraint algebra. So this F shouldn't depends on the derivative of this E1 with this power n greater than 2. So this is actually the condition we get from this one. So that means like this F is only a function of Ki, Ei, partial X E1 and partial X squared E1. and also partial x, of course, also the derivative of K2. However, we just introduce another additional assumption that this f is independent derivative of this K2. And so if we introduce this additional assumption, so the remaining basic scalar are only those 7s. So we only have the 7 basic scalars. However, the point is, like in our theory, we will not consider this S6 and S7 because this S6 contains this Ki in this denominator, and S7 also, yeah, in this S7. So the point is, like in this S7, there will be the, so in this 7 there will be the derivative of this E in this denominator. So we will not consider that because we want our effective Hamiltonian have a regular behavior in the classical regime, because in the classical regime we can choose the coordinates such that this Ki or the derivative of E is there. And then, so that means, like, we will consider the case.
So can you go back to previous slide?
Okay.
So there is this S5 and S7. For me, they looking the same.
Sorry. Yes. Sorry. So here it should be, you are right. So here it should be like S7, S3. Yes. It should be like S3.
Okay, then you would have in the denominator K1. Okay, thank you.
Yes. Or S3 or sorry, let me go to double check later. Okay, so here it is something. Let me just go to, so it is different from this S5. Okay, so thank you for pointing this out. But the point is, like, finally we only consider our f is a function of these 5 basic scalars. And then because f is the function of these 5 basic scalars, you can just commute the Poisson bracket between this one, and it is given by this one. So here fa is just the derivative of f with respect to sa. Okay, and then you can just substitute this result into this one, and also here, so here another point is, like, mu will also be a function of those 5 basic scalars, because you can get from this one, and then you can also write this mu as a general function of these 5 basic scalars. Then you can just substitute the result into the constraint algebra and also this one to do some calculation, and the final result is this one. So we will get this H if it is a function, it depends on this mass function M if, and also a free function R. So here R is a function of S1, so that is E1, and also this mass function. And M if is a function of S1, S2, and S4. So they satisfy these 2 equations. Basically, the first equation comes from the constraint algebra, and the second equation actually comes from this covariance condition. So the second equation, so actually the meaning of this second equation is that mu can only be a function of S1 and M if. And then we just solve this equation, so we will get a different covariant model. So of course, the first solution is this classical theory. In this classical theory, we'll get this mass function, and then you just substitute this result into this Hamiltonian constraint. You will get this one. This is the classical expression of the Hamiltonian constraint. We also have another 3 solutions. So this is this M if 1 and M if 2. So this is the value of this mu, and this is the result of this H. We also have the third M if. So so this is the result of this mu corresponding to this M3. So the point is, like, so because here there are those sine functions, sine of this S2 is K2. So that means like these two models can be related to loop quantum gravity model, because in loop quantum gravity model, this polymerization means we just replace this extrinsic curvature by a sine function. So they can be related to this loop quantum black hole models, and we can choose those arbitrary function mu, lambda per psi, and so on by this mu bar scheme loop quantum black hole. And this is the result. We just choose this lambda to be this one and this per psi to be 0. So we will get this is the first effective Hamiltonian constraint, and then you can just solve the dynamics. So you will get this metric. And this is the result of the Penrose diagram of this metric. So it's very similar to the Rn black hole. And this classical singularity is resolved by this transition region. So this transition region C, which connect a black hole and a white hole. And we also have the second, in the second model, so we have this one. We also choose this one, and this is the result. And we get this Penrose diagram. And in this Penrose diagram, this classical singularity is replaced by a transition surface, this blue line. And by this transition surface, and which connect a black hole to a white hole. And this is the structure of this metric. And for the third one, the point is like, in this third one here, there is also a sine function, but inside the sine function, it is S2 squared. So here, inside the sine function, it is S2. So then, motivated by this mu bar scheme loop quantum black hole, we just choose this lambda S1 in this M3 as the square of this lambda S1 in this M2 and M1. So that means like we do this choice for this lambda and the per psi. So we will get this result. We will get this result. This is the Penrose diagram of this of the metric corresponding to this model, and the Penrose diagram depending on this parameter M0. And so for this GM, the mass of the black hole smaller than this M0, there will be this one, and there is this X equals to X mean. So it is actually a wormhole, and this is the throat of this wormhole. And for this for the black hole mass equals to this M0, so it's somehow like the throat of this wormhole becomes light-like or now. So we have this space-time structure. And in this one, for this GM greater than this M0, so this the throat of this wormhole becomes spatial-like, and we have this region S. So you can, so here the point like this S, it is actually a Schwarzschild ADS, so asymptotically. So once this X goes to infinity, so the metric in this S region becomes a Schwarzschild de Sitter with negative mass function. So that is the this property of this region S. Okay, so finally, let me conclude my work. So in our work, we consider general covariance in the effective Hamiltonian framework of GR. So we first get the sufficient and necessary condition for covariance, and then by some calculation, we get this covariance equation for the effective, and then we just get 3 solutions. Besides classical solution, we get another 3 solutions encoding quantum gravity, this covariance equation, and they have those Penrose diagram. And here it is just some outlook. So for instance, we can consider the dust collapse and matter coupling. And also we have this function R. So here we consider this R equals to 0. But we also want to consider the effect of this function R, and also framework to the model with other symmetries. Okay, thank you. I'm sorry for the internet.
So thank you very much. So we have time for questions.
Okay, maybe I have a short question. So
Yeah, please.
are all those models you presented non-singular? And also, if so, are there singular solutions to those equations that you have studied?
So you mean singular, you mean the singularity, right?
Okay, so this one is singular, still singular.
Yeah, so in this one, there is this time-like singularity, but in the second and the third, there's no singularity.
Okay, thank you. Maybe I have also another short question. So one of your Hamiltonian, I don't remember which one, was complex. Is that right?
Yes, the first one, yes.
So what's the physical interpretation of this Hamiltonian not being real? Have you thought about that?
Yes, that is a very good question, and yeah, so it's true. It seems like in this first one, so we have this complex. So it seems like yeah, it's not like the point is like in this first model, if we want to get a solution, we need to ask this K to be complex, and then we can get this solution. And we still don't know what is the behind the meaning of this complex stuff in this model. Maybe it is related to the self-Drew Ashtika variable, or it is related to the to this theory with a complex Barbour image parameter, or something like that. But we still don't know what is the point in what is the meaning in this model.
Okay, so in this model, the Barbour-Mirzi is real. Is that correct?
Yes. So far it is real. But yeah, but it may be equivalent to some loop quantum black hole model with complex Barbour image parameter. But it might be, but we don't know.
Thank you.
So I have question.
Yeah, please.
On this slide, you have written solutions to the covariance equation. So is it all solutions, or you have, or there is some, you assume something more about this M effective to get these solutions, or this is the complete list of solutions?
You mean this one?
Yeah, so I mean this MF, yes, because you need to compute MF.
Yes.
So do you assume something additional about this effective mass to get this solution, or it's general?
No, it is general. The only assumption here, the only assumption we introduce is this one. So the first is this H if is independent the derivative of K2, and also we don't consider this S6 and
okay.
S7. So yeah, so that is the only extra assumptions we introduced, and then we get this result.
Okay, yes, so this result, yes, but on the next slide, you have a list of solutions. So do they, so is it the complete list of solutions? Oh, this, yes, I think.
No, I don't
No.
think so. The point is like, so you can say, so on this M if it is actually a nonlinear partial differential equations, third order, right?
Okay, so it's complicated.
Yeah.
Okay, so you have
Yes.
Okay, thank you. So
Okay, thank you.
Are there other questions? Okay, so I don't hear. So let's thank Cong for a very nice talk, and thank you very much. Thank you.
Okay, so thank you. So I'm sorry for this internet. Yeah, so I don't know why it happens today, but I hope that